So in this lecture, we're going to discuss regarding the genesis of the first order p.d.e. Means the how the first order differential partial differential equation are classified into. So first of all, we need to understand what does it mean of a partial differential equation. So by a partial differential equation, we mean that, and this partial differential equation will denote by or say by short name, that is p.d.e. We mean that an equation containing of the form, that is f of x, y, t. There are many variables: theta x, theta y, theta z, so that theta t, and so on is equal to 0. Or it also may contain theta x, t, and so on. That means it will contain the, what is theta x will represent is del theta by del x. So theta is actually a function of x, y, z, and t. It is a function of continuously partial derivatives of order n. That means all order of the derivative is exist. So this form is involved two or more independent variables. It will involve many variables, independent variables, x, y, z, x, y, t, and all sort of them are independent variables here, etc. And the one variable that is theta, I should say one dependent variable, theta, which is a function of x, y, t, and etc. in Cn, in some domain D. A domain means it is a connected open set. That is the meaning of domain. And what is this Cn? A Cn is the set of all functions whose they are continuous partial derivatives of all order is exist. That is Cn. And it's also its partial derivatives that is theta x, theta y, theta t, and so on, theta x, y, theta x, t, and so on. All of them belongs to Cn. As I told you, where Cn is the set of functions possessing continuous partial derivatives of order n. So thus a p.d.e. is the relation between dependent variable theta and sum of its partial derivative at any given point x, y, z, or x, y, t, and x, and so on. Now in the partial derivative, so this in general the partial derivative is represented in this manner. Now what will be the definition of order of the partial derivative? So order of PD. The order of the differential equation, or I can say a partial differential equation, to be the order of the derivative of highest order n occurring in the equation. So whatever the highest order derivative is occurring into the differential equation, it is known as the order of the differential equation. So here what is the title is the genesis of first order linear differential equation, or I can say first order partial differential equation. The order means we are talking about the partial differential equation which involves only first order derivatives. For example, zx plus zy equal to z. So this will, zx is a z which is a function of x and y, and del z by del x is the partial derivative of z with respect to x, which denoted as zx, and del z by del y is the partial derivative of z with respect to y, which denoted by zy. So this is the example of first order partial derivative. Now there is a classification of first order partial derivatives are there. In that first one is the quasi-linear p.d.e. Quasi-linear p.d.e. A p.d.e. is said to be a quasi-linear if the derivative of the highest order which occur in the equation are linear. That means whatever the partial derivatives is there, they are occur in the linear form. That means we generally denote this notation. P is the stand for del z by del x, and Q is the stand for del z by del y. These are the majority of every book is following the notation. If z is a function of x and y, then this is P and Q are the first order partial derivatives which are exist in the some PD. If they are linear in that PD, then that equation is called quasi-linear equation. So I can say the quasi-linear equation is of the form P of xyz into P. The small p represent this. Capital P is the function of x, y, and z. Q of x, y, z into Q is equal to R of x, y, z. So this equation, it is actually a linear in P and Q. So that's why this equation is a quasi-linear equation. For example, if I can tell you an example, let's say it is x square plus z square into P minus xz into Q equal to z cube x plus y square. So this is the one of the example of quasi-linear equation where the equation is linear in P and Q. A next definition is a semi-linear. Semi-linear p.d.e. So what is the definition of a semi-linear p.d.e? A quasi-linear p.d.e is said to be semi-linear if the coefficient of the highest order derivative does not contain either dependent variable or its derivative, either a dependent variable or its derivative. What we have learned as a quasi-linear, the quasi-linear equation is of this form: P, capital P into P, capital Q into Q is equal to R, where P, Q and R, all of them are the functions of x, y, z. But what is the definition of a semi-linear says that equation, the coefficient of this first order derivative will be independent of the dependent variable. So here the dependent variable is z, because z is a function of xy. That's why the form of semi-linear will be, so this it is of the form, it is of the form capital P of xy into P plus capital Q of xy into Q is equal to R of xyz. R may be a function of xyz, but as per the definition, it says that the coefficient of P and coefficient of Q will be independent of z and its derivative. For example, if I can write the example, e power x into P plus xy into Q is equal to x into z square is an example of a semi-linear partial differential equation. So if I repeat, the first order partial differential equation is to be a semi-linear if it's linear in P and Q, and the coefficient of P and Q are the functions of x and y only. That is another way is to looking at this definition. The next one is the definition of a linear differential equation. Linear p.d.e. So a semi-linear p.d.e. is said to be linear if it is linear in the dependent variable. It has to be linear in the dependent variable its derivative. Okay. So first of all, any linear equation first has to be a semi-linear. What does it mean of a semi-linear differential equation? It coefficient of the order derivatives are there which are independent of the dependent variables, the coefficient of that. So what is the form? So it is of the form, if I can say it is a first order, then it is of the form p of xy into p, q of xy into q is equal to r of xy into z, because it says that all the things, that means it is linear if it is linear in dependent variable also, and it is semi-linear. So semi-linear, the coefficient will not contain this, plus you have here s of xy plus some function of xy there. So it is of this form. For example, if I can say that y into p minus x into q is equal to xyz plus x. So all the power will be a linear one. That means its derivative is of all power is 1 and also with the z. But here you can say that it is maybe possible that it is z square on this side. But in linear, everything is of degree 1, what I can say. So that is the classification of first order linear or first order partial differential equations is there. And the p.d.e which is not quasi-linear, it is called a non-linear differential equation. So the next definition I can say it is a non-linear p.d.e. So in short, it says that a p.d.e which is not a quasi-linear is said to be non-linear. So the form of the non-linear is, if it is, can say it is a partial differential equation of a first order non-linear, then it is of the form f of xy z p and q equal to 0. So this is the non-linear first order p.d.e is of this form, and it may be of any of the type. For example, I can say pq is equal to z. So this is the example of non-linear first order partial differential equation. So these are the classification of the first order linear partial differential equation is there, and non-linear. In the first 2 units, we are discussing only a first order linear partial differential equation, linear and non-linear. And in the 3rd unit and the 4th unit, we are discussing regarding the second order partial differential equation, how to solve it. So the first 2 units, or I can say a first chapter of your book, is related to how to solve and how to form a first order partial differential equation. So general form of the first order partial differential equation can be write in this form, f of xyz. So I may write that the most general form of first order p.d.e is f of xyz p q equal to 0. So this is the form of first order partial differential equation. And partial differential equations are arise in very large varieties of the subject, in the geometry, in physics, in mechanics, and in mathematics. There are varieties of subjects in which the partial differential equations are involved, but because there are majority of the all functions are depends on more than one variables, they are changing that value due to the many of the variables. So that's why it's very important for those who are doing the applied mathematics point of view. It is very important subject to learn this. So first we have to learn that how to eliminate the arbitrary function from the given equation. The first example that I am taking here is the surface of revolution. So in that, many surface of a revolution about the z-axis is of the form z is equal to f of r, where r is x square plus y square raised to 1 by 2, or I can say square root of x square plus y square, where f is an arbitrary continuously differentiable function. What is our objective? Our objective is to find out the differential equation whose solution is this. Okay, so what is our objective is to calculate the differential equation whose solution is the surface of revolution. So I can say that many surface of revolution with z-axis as the axis of revolution are of the form this. So to get the differential equation, we need to involve the first order partial derivatives. So if I differentiate this z is equal to f of r with respect to x, what is the situation we have here? Z is a function of r, which is we have a functions of one variable only, and r is a function of two variables, that is x and y. So ultimately your z is a function of x and y both. Okay, so on differentiating, z is equal to f of r with respect to x and y respectively, we get what we will get del z by del x. As I said that z is a function of r, so it is equal to f dash of r because it is only one variable is there. So I should say that is del z by del x is df by dx, sorry, dr into del r by del x. As per this, you have to go via this path. So that's df by dr, we just writing as f dash into del r by del x, and del z by del y again it is del f dash r into del r by del y. Now you just see that r is equal to x square plus y square raised to 1 by 2. So del r by del x is 1 by 2. Okay, so if I take the partial derivative of this one, it will be 1 by 2 x square plus y square raised to 1 by 2 minus 1 into a derivative of x square plus y square will be gives you 2x. This 2 will get cancelled out, and hence we'll have x upon x square plus y square raised to 1 by 2. Because it is 1 by 2 minus 1, so it will gives me minus 1. I will take that as in denominator, so that will gives you x by r, because x square plus y square is to 1 by 2 is r. So del r by del x is x by r, so that I am putting the value here. That will gives you f dash of r into x by r. Here del z by del y is equal to f dash of r into, in the similar calculation, in the same type of calculation as you did for x, if you change with y, you will have y by r. Now we have to eliminate this f dash from this 2. So I will find out the value of f dash, and we know that this we have represented as p and this one we have represented as q. So that I can write down p r upon x if I can find out the f dash value from this. And from this it is f dash is q r upon y. So therefore this pr upon x is equal to qr upon y. And you can just see that x square plus this r will get cancelled out, and this will implies that yp minus xq equal to 0 is the required differential equation which does not involve the function f. So which is the first order, I can say, which is a p.d.e of first order satisfies by the surface of revolution. Of the form which is given here, that is z is equal to f of r, and r is a function of x square plus y square under root. Let's have the another example. So in that we'll taking or dealing with some different example. Consider the surface of the form f of uv equal to 0, where u is equal to u of xyz and v equal to v of xyz are a known function of x, y and z. So they are the known function of x, y and z. And where f, capital F, is an arbitrary function of uv, and capital F is arbitrary function of u and v. Now what we need to find out here, we need to calculate the first order derivative or first order partial differential equation which does not involve the function f. So whose solution is this function f? That we need to calculate. Now what is the situation here you have given? We have this function f is a function of two variables, u and v. And u and v are the functions of three variables, that is x, y, and z. But what is the situation is given, what we have, this z is a dependent variable. So z is depends on x and y. Okay. So the situation is the u is a function of x and y, but among that x and y are the independent variable, and z is a dependent variable which depends on x and y. So when I differentiating this f of u v equal to 0, we'll have certain things to deal with. So let us write that on differentiating f of uv equal to 0 with respect to x and y, treating z as a function of x and y. We have to treat the function z as a function of x and y. So what we will get if I differentiate this f? So you have to go with the two paths. The first one is f with respect to u, and then u is with respect to x. So it is del f by del u into del u by del x plus, but what is the situation here? The situation is this u is a function of x, y, z, but z is depends on x and y. Okay, so it will be del u by del x into del x by del x, and del u by del y into del y by, sorry, del y by del x plus del u by del z into del z by del x. So this is the situation you can have, plus del f upon del v, the same situation we have here also, del u by del x, sorry, not u but it is v, into del x by del x plus del v by del y into del y by del x plus del v by del z into del z by del y equal to 0. Now what will happen to del x by del x? This will tends to 1, and since y and x are independent variable, this will tends to 0. Here is also this will tends to 1, this will tends to 0, and this will be p and this is q. So finally, what is the situation or what is the expression we get is this del f by del u into del u by del x, I may write as ux plus, this is 0, this term is, second term is 0, the third term is u z into p plus del f upon del v will be u, sorry, not u but it is v x plus vz into q equal to 0. And if I differentiate the same quantity with respect to y, here we got this one with respect to x. If I differentiate with respect to y, then we will have by replacing x by y. That is the change we can have. So it is gives you del f by del u into uy plus uz into q. You will have plus, not, here is also x, so this is my mistake, here it should be x here. because we are differentiating with respect to x only. So this is not q, but this is p. So this value is p here. And hence here it is q, and this is del f by del v into ux plus v's, not u, but it is v, z q equal to 0. Now we have these two equations, equation number 1 and equation number 2. We need to eliminate this del f upon del u, del f upon del v from these two equations. So what we have to do, we have to use, so on eliminating, del f upon del u and del f upon del v from this equation, we obtain. What should we do to eliminate this? There are many ways to do this one. So this is the equation of this type: a1x plus b1y equal to 0, a2x plus b2y equal to 0. The question is to eliminate this x and y from this. Okay, that is the question. Here x and y is this, del f upon del u, del f upon del u. So what you will do is you can just multiply this quantity to this equation, or you may multiply this quantity to this equation, the second equation. So that will eliminate this del f upon del u, which gives you the equation in terms of only p, q, u, x, uy, uz. So this will gives you determinant of, because this will gives you a1, b1, a2, b2 is 0. So that's why due to that we'll have ux into p uz, vx into p vz, uy plus p uz, vy plus, sorry, not p here, it is q, q vz equal to 0. To simplify this one, and you can open this determinant, you will have ux plus p uz into vy plus q vz minus vx plus p vz into uy plus q uz equal to 0. Now if you simplify this one, what you will get? You will get ux, uy, q ux vz plus p uz vy plus pq uz vz. On this side, all the terms which are of negative sign, that is vx, uy, then plus, sorry, minus q vx uz minus p vz uy minus pq uz vy equal to 0. This get cancelled out. So we'll write down the constant terms, the coefficient of p and coefficient of q separately. So first let's write the coefficient of p. What you will have this and this, that is uz vy minus vz uy. plus q. We'll write that ux vz minus vx uz equal to, I will take this two quantity on the other side, that is vx uy minus ux vy. Now you just observe that what is this quantity, that is I have written in the this bracket, that is p. And if you just recall that what is del f del g upon del xy, the Jacobian of fg with respect to xy, that is we know that it's fx fy gx gy. So it is nothing but the fx gy minus fy gx. So if you compare this with this one, then this is nothing but the determinant of uz, sorry uy, sorry if I can say, yeah, uz, here it is vy, and here if I write vz, this is uy. Okay, so it is uz minus this. So this we can write in this form plus q. This one I can write as vz ux uz so it is vz into ux and vx is here. Okay, and is equal to, on the other side, that's this quantity we can write as uy, and here I may write vx. Here if I can write ux, this is vy. So as per this one, if I can simplify, then this is p into del u del v upon del zy plus q into del v del u upon del zx equal to del u v upon del y del x. So this is the equation we got, which is first order partial differential equation, satisfies the means the equation f of capital F of uv equal to 0, eliminating this function f from this. Let's have the third type of example, that is known as a functional dependent. Functional dependency. So let u v is equal to v of xy be a non-function of x and y. So this v is a known function, and let u equal to u of xy be a function of v alone and not involving x and y explicitly, not involving x and y explicitly. So this is the third case to form a partial differential equation. So that is, we are looking at the situation, that is u is a function of v and v is a known function of x and y, where h is an arbitrary function and h is actually belongs to C1, that is a continuously differentiable functions. So on differentiating this equation with respect to x and y, on differentiating u equal to h of v with respect to x and y, what we will get? We'll get ux is equal to h dash, or I can say del dh by du v into del v by del x, because what is the situation is this u is a function of v and v is a function of two variables x and y. So that's why we have this, and if we are differentiate with respect to y, then we have dh by du, sorry, dv and del v by del y. So this I can write down as h dash of v into vx, and this is h dash of v into vy. Now we have to eliminate this h dash of v from this. So I will find out the what is h dash of v from this, that is ux upon vx. Here it will be uy upon vy. If you want to eliminate this h dash from this, then you will have expression ux upon vx is equal to uy upon vy, which will give you ux vx minus vx uy equal to 0, and ux vy is there. So this is what? This is actually a Jacobian of uv upon xy equal to 0. So that is the first order PDE is there in the form of u. Okay. So this is the third type of example is there, which eliminate this, the function, arbitrary function h. The fourth type function is actually a Euler's function, or one can say Euler function, Euler's theorem. If you have remember, which you have discussed in your SY-BSc class in the for the homogeneous function. That is, first of all, let us recall what is the definition of homogeneous function. A function f of xy is said to be homogeneous function of x and y of degree n if it will satisfy this equation, that is f of lambda x lambda y is equal to lambda power n f of xy for any lambda and for any xy in the domain. And we know that a function f or function z is equal to f of xy, which is the, let z is equal to f of xy be a homogeneous function of x and y of degree n, then by Euler's theorem, what we can say, if you have remembered your Euler's theorem for SY-BSc class, you can say that x into fx plus y into fy is equal to mf. If m is the degree, here I have taken a degree is n, so that is nf. So this is the partial differential equation which satisfies the function f, which is homogeneous function. So this is another way to looking at the situation. So what we have did in this examples which we have discussed from 1 to 3, and this is the fourth one.